Hello, today I'm going to talk about what's wrong with modern physics. Now, if you talk to a physicist, they'll say there's nothing wrong with modern physics. They talk about exciting breakthroughs. They popularize the different theories like string theory and so on. But you know, the explanations that they give really are very far from the physical understanding that physicists have. They're kind of pulling the wool over your eyes. If modern physics is accurate, then the world is exceedingly complicated and only very intelligent people with very different ways of thinking can understand what's going on in the physical world. Physical world is not simple at all, despite what some popularizers would like to say. If you get into the details, you'll find that it's exceedingly complicated and not simple at all. So does this state of affairs have to be as it is? Let's consider the question, what is an explanation in physics? And where we're going is to try to characterize the explanations that are now given in modern physical theories. Here's an observation that Newton made. The moon falls just like objects we see on Earth. I can explain this statement with the following picture. Here is the Earth. Here is the moon. And the moon moves around the Earth in a more or less circular orbit. Now, as the moon is moving around, it's actually moving towards the center of the Earth. It's just moving fast enough so as it falls towards the center of the Earth, it keeps away from the Earth and never actually reaches the center of the Earth. So the moon is continually turning towards the center of the Earth like it's falling, but it's going fast enough so that it doesn't actually fall to the Earth. So the idea is that the moon is falling around the Earth. So as I said, this is Newton's idea. And Newton said, well, it's falling just like objects we see on Earth. So maybe the same thing is making it happen. We can attribute the motion of the moon and planets to attractive forces, just like the attractive force that we see on the surface of the Earth. Newton's equations plus an inverse square force law actually gives us the motion of the planets. These equations predict orbits which agree with astronomical data. Okay, so what's going on here in this explanation? This is a wonderful explanation of the orbits of planets. First of all, we start with an analogy. We compare something that's not so accessible with something that's very accessible. The forces that create falling objects that we see on the Earth. Okay. This suggests a familiar or intuitive model that these same forces that we see on the Earth also are responsible for the motion of moons and planets. Okay. And this can be translated into mathematics, and this describes behavior that's consistent with measurements. So we have this kind of step-by-step process that starts with an analogy and leads to what we would consider a great explanation of what we observe when we watch the planets in the sky. Okay, let's give another explanation in classical physics. Gases consist of atoms that behave like tiny billiard balls moving around in mostly empty space. And of course, you can't see gases, and there was a lot of physics that went into this idea about gases. But once you have this idea, you can run with it, and you say that heat and pressure are due to atoms bouncing off the walls. As the atoms bounce, they excite the atoms in the wall and cause them to oscillate, or they produce forces on the atoms in the wall. And we can understand heat and pressure in terms of this picture. All right, now, there's a statistical distribution of particle energies, which can be worked out with on the basis of some simple postulates. And this statistical distribution tells us that pressure times volume would be proportional to temperature. And this agrees with experimental data. Okay, so again, we have the same process. We start with an analogy. This suggests an intuitive model that translates into mathematics, which describes behavior that's consistent with measurements. Okay, so this is kind of a classical flow when you in classical physics in trying to explain phenomena. You can see the importance of analogy, that we have something that's not so easy to understand, gases which are invisible and consist of very, very small constituents, and we're relating that to something like a billiard balls on a billiard table. It's very accessible and easy to grasp picture of what's going on with the atoms in a gas. All right. Now, there are other analogies in physics. Light is like a stress wave passing through a material. This was Maxwell's insight. In some of the language used in electromagnetics, like the Maxwell stress tensor, is reminiscent of this type of, this way of thinking that Maxwell had about light. Atoms are like mini solar systems. This is the Rutherford model that Bohr quantized. But you think of atoms as a nucleus with electrons spinning around. Space-time has a topography. You think of space-time as curved, and that curvature is caused by gravity. Just like you can talk about the curvature on the surface of the Earth, you have the curvature of hills and so on. There's a topography, and this topography is defined by equations. In fact, Gauss, who invented differential geometry, was using that in terms of surveying. And the same differential geometry can explain Einstein's general theory of general relativity. You have differential geometric equations, same type of equation, similar type of phenomenon. Okay, all these analogies are limited and ultimately break down, but they are useful, and they give a very intuitive, easily graspable picture of the phenomenon that they're trying to explain. They help us visualize and provide a context for describing the unknown. So what I'm going to argue is that modern physics gives us no context at all, and also does not enable us really to visualize. Modern physics explains in a different way. Let me try to explain how modern physics explains. Here's an example. You could say that this is the first example of real modern physics as it's currently practiced. And I can say that modern physics is agnostic in the following sense. Instead of finding visualizable models, modern physics solves mathematical puzzles. Look at Schrodinger's wave equation. All right, so here's the puzzle set up as Schrodinger saw it. It's known that particles interfere like waves. So particles have properties, waves have properties. Particles have energy, momentum, and Newton's laws relate to energy and momentum. Okay. So waves have frequency, and the Planck was the first to postulate that there's a relationship between energy and frequency. And Einstein picked up on this also in the explanation of the photoelectric effect. If you make this correspondence between energy and frequency, it follows that momentum should relate to 1 over wavelength. That this correspondence follows from the relationship between energy and frequency. Now, we have an equation that relates energy and momentum. So over on the wave side, we should have some kind of equation that relates wavelength and frequency. So from this analogy, we obtain an equation. Now, the analogy is purely mathematical. We don't even know what's waving. We just get a mathematical suggestion from the similarities between particle and wave. There's not a realizable picture. We don't see anything waving. We just have an equation that relates quantities. Now, later on, Bohr found that you could interpret the thing that's waving as probability, but probability doesn't wave. There are a lot of paradoxes in that type of identification. So really, the identification is mathematical. It's not in terms of a realizable model or picture. Dirac said that since Schrodinger, fundamental physics can be characterized as a quest to make mathematical puzzle pieces fit into beautiful shapes. So that's what modern physics is. It's solving mathematical puzzles. But what do the shapes represent? And what's making it happen? Modern physics idea is agnostic. Don't ask, shut up and calculate. And David Merman's famous quote, often attributed to Richard Feynman. So you just have shapes, and the shapes are just there, and you try to see patterns in the shapes, but don't ask what they represent, and don't try to create some type of visualizable or intuitive model of what's actually going on. It's purely mathematical correspondence. Could it be that the mathematical descriptions are all that we're ever going to get? No, I think perhaps the majority view is yes, that now physics has been reduced to mathematics. We're beyond the realm of intuition, and that's as good as our understanding of the universe is going to get. So our familiar model is obsolete in physics. As physics moved on to a new realm beyond intuition, beyond realizable models, beyond something that relates physics to things that we can see and grasp in an everyday intuitive way. Now, there doesn't appear to be any particular reason why intuitive analogies should always exist. So that's an argument in favor of this modern view. That why should middle world behavior resemble macro world and micro world phenomena? Richard Dawkins came up with this term middle world to describe the world that we see, the familiar world. And why should this behavior be in any way comparable to the behavior we see on macro scales, on astronomical scales, and on micro scales, on the scale of the atom? Or maybe there's no way to compare the familiar behavior, but behavior that we can intuitively relate to, and this type of behavior in the macro and micro world. And who needs a model? Isn't the mathematics good enough? Again, this is kind of the prevailing view in physics, that if you have a mathematical model that works, that's good enough. Why do you want any more understanding than that? Now, I would say that mathematics is a soul of physics, and that's true. But mathematics without a realizable model is in some ways like a disembodied soul. It's not satisfying to a lot of people. Maybe modern physics or people who have an abstract cast of mind are satisfied with this if they can have the equations. But for many of us, we don't really feel that we can grasp. If we can't relate it, if we can't fit it in, if we can't make an analogy with the rest of our experience. All right, now I think there is some hope for analogies. Intuitive analogies have worked far better than we have any right to expect. I mean, should we expect that molecules work in a very similar way to billiard balls? Should we expect that atoms, in some ways, have behavior very similar to the solar system, or that light can be compared with the behavior of a stress wave? These are analogies to everyday accessible phenomena that go far beyond everyday accessible experience, and they work very well. Einstein said the most incomprehensible thing about the universe is that it is comprehensible. So there seems to be something deep about the way the universe is arranged so that incomprehensible things can be compared to comprehensible. And if you think about modern physics, Einstein's theory is by far the easiest to create an analogy with. Einstein's theory of gravitation is that space is curved, which we can readily comprehend in terms of the curvature we see of hills and so on, items on the surface of the Earth. Now here's where I bring in some conviction that God created man in his image as a creative being, able to think his thoughts after him. If we think about the universe in these terms, then it seems quite reasonable that the structure of the universe, the way the universe works, should be in terms that are that's comprehensible, graspable, accessible to man. And this is a consequence of this sort of viewpoint, that God created man in his own image, able to think his own thoughts after him. And I would like to advance the idea that modern technology may become a fruitful source of analogies. Technologies like computer, wireless communication, things like this. We're able to manipulate things in our world in different ways. And we understand relationships, and we can understand these in a concrete way that can be manipulated. And computers give insight into intelligence. Wireless communication may give insight into the transmission of elementary particles. So I'm suggesting that rather than analogies with everyday phenomena like billiard balls or stress media, we can begin to think of analogies in terms of technology. And I believe that these analogies may continue the classical mode of explanation where we can relate inaccessible and remote and very large and very small phenomena to phenomena that is ready to hand. So that's my presentation. Thank you for watching.